Now we want to describe the sphere, a sphere of radius A. Whoa, a sphere of radius A, centered at the origin, and that sphere we've already seen could be represented by rho equals A in spherical coordinates. What if we wanted to represent the sphere in cylindrical coordinates? So this is just any sphere with the radius A. Now we're going to work this back in to the situation we've been talking about, where we have a spherical shell from rho equals 2 to rho equals 4. But right now we want to describe any old sphere of radius A, centered at the origin, in cylindrical coordinates. Okay, well, it should be clear, and I'm not going to give this any explanation, it should be clear that in the r theta plane, where z equals 0, the sphere occupies the circle of radius A. And that circle can be described, as we know from polar coordinates, by 0 less than or equal to theta less than or equal to 2 pi, and 0 less than or equal to r less than or equal to A. Okay, so right here is a picture of the intersection of that sphere, the sphere radius A centered at the origin, with any plane including the z-axis, any plane that includes the z-axis. And this plane, any plane which includes the z-axis, is going to make some angle theta with the positive x-axis, measured in the counterclockwise direction, of course. So the intersection with any plane is going to look the same. It's going to look like this. You're going to have a circle of radius A, r, you can have an r-axis here, okay, and a z-axis, because of course we said that the plane includes the z-axis. Okay, now down in the r versus theta plane, we'll have some point r star, theta star, 0. We imagine, in other words, partitioning from 0 to A, partitioning the interval from r equals 0 to A into a bunch of smaller sub-intervals. And we think of a typical interval here, which contains the point r star, theta star, 0. And theta star, of course, is whatever theta happens to be right now, depending on where we, the orientation of the plane, the vertical plane with which we cut the sphere. Okay, and nothing that we do here is going to depend on theta until we get down to the integral. Within a typical partition, where we have coordinate r star and also theta star, and of course we're down in the r theta plane, so z is 0 along the r axis here. What are the limits on z? In other words, here we are in the plane. How high do we have to go to get up to the sphere? How low can we go and still be on the sphere? Okay, z will go for this given r, value r equals r star. It'll go from a point down here to a point up here. We go to a different subinterval in our partition. We'll go from a different value of z to a different value of z. Okay, well, if this is r star, this distance from here to here, or this displacement is r star, then what is the value of z down here? What is the value of z up here? We can see it easily if we just look at this triangle right here. Clearly, this point here will give us the z-coordinate of our point here. Okay, the point here projects straight over. This is a right angle. Here's our z-coordinate. And this side of the triangle goes from z equals 0 to whatever our z-coordinate is here. And this is a right triangle. Okay, now This side here is vertical, it's perpendicular to the r-axis, it's parallel to the z-axis. So if this distance here is r star, which it has to be if those are the coordinates of the point, then this distance here has to be r star. So now we know this side of our triangle and we know the hypotenuse. Okay, well, now that we know the hypotenuse and this leg, we can easily find this leg, and this leg will correspond to our z-coordinate, in the sense that the absolute value of our z-coordinate at this point is going to have to be the square root of a squared minus r star squared. And that's what I've written here. The r star squared is a little hard to read, but that's r star squared. And of course, at this point, z equals negative square root of a squared minus r star squared. And there's symmetry here, so if we do the same thing with this point, we could construct a triangle in the same way and project over. But we would find that z is going to be plus the square root of a squared minus r star squared. So for any point where r has the value r star, the sphere will go from negative the square root of a squared minus r star squared up to positive square root of a squared minus r star squared. Now at either this point or this point, the absolute value of z, which is going to be the side of this triangle, or the vertical leg of the same triangle constructed above the axis, magnitude of z at both those points is going to be a squared minus r star squared, so that z could be as low as negative a squared minus r star squared, as high as square root of a squared minus r star squared. Okay, so r can go from 0 to a, theta can go from 0 to 2 pi, and for any r and theta, z will go from negative square root of a squared minus r squared to the square root of a squared minus r star squared. So these inequalities define our sphere. Okay, and that isn't really too awfully difficult. Okay, now we want to move on to the description, having seen how to describe any old sphere in, make that minus look a little better, any old sphere centered at the origin. We want to think in terms of two specific spheres. Okay, the sphere of radius 2 and the sphere of radius 4 that we've been dealing with up to this point. So what does it look like now if we slice this spherical shell? Pretty thick shell, but this spherical shell, this radius 4 sphere with the radius 2 sphere cut out of its center. What does it look like if we slice that parallel to the z-axis? And it should be clear that we have a picture very much like this one, with z here and r along this axis. That this corresponds to any theta so that's z versus r for any theta, and that we have to describe this figure in terms of vertical cross sections. So we'll get to that in the next video. That's where we're headed. Make sure we understand this. Make sure we understand why we're going to this picture.